Okay, so, I mean, that's important, obviously, in both the written response and the multiple choice, okay? I'm not gonna ask you what's the definition of a vector quantity, that's certainly not important, but you need to know that in order to know when it applies or not. Okay, around that same time, we also talked about V equals D over T. Okay, while there aren't any written response items dedicated solely to V equals D over T, it still comes up. Okay, it would be part of projectile motion for the horizontal component. You'd have to use it there. Sometimes on a position versus time graph, you have to use it. Could even come into play like for an echo question in the waves unit. It comes up. It's just something that we need to know how to do, but I'm not going to have a 4-mark final exam written response question that is nothing but V equals D over T. All right, so we do have to remember that when V doesn't have the arrow over top of it, it's scalar, so that would be speed, and that would be distance divided by time, also no arrow over top of it. When it has an arrow over top of it, it's velocity, that's displacement divided by time, which we can expand out. Lots of times we need to do that on a graph, okay? Final position minus initial position divided by time. Okay, questions so far? Don't be afraid to ask as we go, guys. Now's the time, right? Okay, then we talked about graphing. Graphing is definitely on the final exam in both sections of the exam, both in written and multiple choice. Okay, so there could be some interpretation and there could be some calculation. Could be, will be, what's the difference? Okay, so that will be on there. Okay, I could ask you for a linear graph to use y equals mx plus b. That could be a position versus time or a velocity versus time graph. We need to know what that calculates in both, right? If it's a velocity versus time graph, okay, then the slope represents something different, as do y, okay, b, and x. Well, x is the same because it's time in every graph we've ever done. Okay, but on a velocity versus time graph, y would be the final velocity, b would be the initial velocity. What's the slope? It's acceleration, because it would be the change in velocity, y, divided by the change in x, time. Okay, change in velocity over time is acceleration. If it was a position versus time graph, then y would be your final position, b would be your initial position, x would still be time, and your slope would be velocity, because it would be the change in position, right, divided by time. Okay. So little things like that, they need going over. They'll probably come right back to you. It's just been a while since we did. Okay, so just quick review of those two types of graphs. Okay, what's that object doing on that position versus time graph? It's moving. Yep. At a constant velocity in a positive direction. Yeah. Okay. Moving at a constant velocity in a forward direction or positive direction because we see that its position is changing uniformly. That is by the same amount per time interval. Okay, and then if we have a velocity versus time graph and it's linear, okay, like this one, then that would be an object that is doing what? It's accelerating. Its velocity is increasing over time, which is why when we calculate the slope, it's essentially final velocity minus initial velocity divided by time. That's where that formula comes from. Okay, or you could have an irregular graph. Okay, during this part of the graph, what's the object doing?
Not moving.
Right, traveling at a constant speed, right? Its speed is constant. Okay, if that line was down on the x-axis, then it would be not moving. Okay, on a position versus time graph, that's what not moving looks like, but this is a velocity versus time graph. The velocity is not changing, so it's moving at a constant velocity. Okay, little interpretation, things like that could certainly come up in like a multiple choice question or something. Okay, on this type of graph, we were also asked lots of times to calculate the displacement of the object, okay, and that's where we want to use average velocity times time, and we talked about how calculating the area between the line and the x-axis is taking the average velocity. So for this part here, okay, the velocity is constant, so taking the base, the time, and multiplying it by the height, the velocity, I would get the displacement. Here, because the velocity is changing, I would use the change in height divided by time, or base times height over 2, because the average velocity is halfway between the initial and the final. Okay, that's why that whole area under the line thing works. You're really just using B equals D over T. All right, so stuff like that certainly could come up on your final exam. All right, then acceleration. We got a lot of acceleration formulas. Okay, expect that you'll probably have to use them. There may not be a dedicated question on acceleration, but it could certainly be part of other questions. It's part of projectile motion. It could be part of Newton's second law, okay, because mass times acceleration is net force, so I could make you do an acceleration question and then calculate force after that. Okay, so it does come into play on quite a few other concepts, but would I necessarily have a question on the written response that's just acceleration? I'm leaning toward probably not, okay? But it is certainly involved in a lot of other questions, so you definitely need to know when to use all of the formulas. Best way to do that, write down your givens, okay? Match them up with what you've got. Okay, so those are the ones that we went over, okay? And we also did this one, D equals VF times T minus 1/2 AT squared. And we also did this one where V is VF plus VI, sorry, not VF. I'm drawing a blank on that formula, guys. Oh crap, don't do that. That was the wrong thing to push. Drawing a blank on the other formula. VF plus VI over 2 times T, right? Is D. That's where I messed up. D is supposed to be over here. Okay, we also have this one. D equals VF plus VI over 2, okay, times T. That's just average velocity times time. All of those were formulas that we went over in the acceleration part. Then vector component addition. Bet on it, there will be one of those. Okay, and it'll either be one involving force, which is a vector quantity, or it could just be a position one like we did in class. Okay, we did some force ones in class as well. Okay, so make sure you've gone over, drawing your diagrams, calculating your x and y components, adding your x's, adding your y's. You guys were getting really good at that by the end of the unit, so I'm not worried about that part of it, but it's certainly something to review and do if you practice problems. Okay, so why don't we try that? Okay, so problem on the board. Okay, give that one a try. You're adding 10 meters at 30 degrees north of west and 12 meters south. That's 12 meters south. Okay, give you a couple minutes on that one, see what we remember. Okay, so let's have a look at that one. So if we're drawing the diagram for that one, okay, we've got, it was 10 meters north of west, okay, so it's going to be up this way at 30 degrees, but obviously it's not going nearly as far north as the next vector is going to go south, okay, so we're going to go right past our starting position north-south and end up way down here. Okay, so our diagram should probably look something like that if it's drawn reasonably to scale. Okay, then we've got to calculate all of our x's and y's. Okay, so the first triangle, the 10-meter triangle, if I'm going to calculate the horizontal or x component here, it's the adjacent side to the angle. So I calculate it with cos of 30 times 10 meters gives me 8.66 meters to the west. Okay, and then the y component is opposite, so that would be the sine of 30 times 10, which is 5 meters north. Okay, our second vector is vertical, so it has no x component, okay, but it does go 12 meters south. All right. So when I want to calculate my final triangle, I can draw it either way. You could draw it inside here if you wanted to, and that's fine. Okay, but the sides are still going to come out the same. The overall y component, I'm going to have to take the 12 meters south and subtract the 5 meters north. So I'll be left with 7 meters south. And then for the x component, that's easy because I only go west in the first one. So it's just equal to the first x component that I found. That's 8.66 meters west. So now I've got the x component and the y component for my resultant triangle. If I do Pythagorean theorem with those two, then I'll get my overall displacement's magnitude. I still need to find its angle. So the way I drew this triangle, it'll be the inverse tan of x over y. If you drew the triangle the other way, it'll be the inverse tan of y over x. And so what we'll end up with is that we will have 11 meters at 51 degrees west of south, okay, or at 49 degrees south of west, okay, whichever one you ended up calculating, okay. Sorry, 39, yeah, right, because it doesn't add up to 100, it adds up to 90. All right, where's my coffee? All right, making sense? Other than Coder, you can't think today? Okay, ringing a bell then? Everyone's good with the vector stuff? Okay, could come into play with either Unit 1 stuff or Unit 2 stuff if it's a net force question. Okay. All right, after we did vector addition, okay, then we moved on to projectile motion. Okay, and there were two kinds. But I'm not going to test them both on the final because that takes too long. So which one do you think I'll test? Projected horizontally or projected at an angle? Angle. Yeah. Okay, definitely going to be a problem-solving question. Projected at an angle. Okay, projectile question. So things we need to remember about projectile motion. The horizontal component of projectile motion is uniform velocity. So the object travels at a constant velocity. So the x part of projectile motion is v equals d over t. Okay. The vertical component is obviously affected by gravity and thus is accelerated motion. So any one of our acceleration formulas could be useful for that part. Okay. When does the maximum height occur for a projectile? Halfway, yeah. Halfway in terms of time, okay? Halfway in terms of horizontal displacement, all of that. It's exactly halfway through because it's going to make that arc. Okay. All right. So there was this kind, the projected horizontally kind, where the initial velocity would be 0. Could still be some multiple choice about that, but there won't be a big problem to solve. Okay. So we could use that to calculate like the height of the cliff, or how far from the base of the cliff it is, or how fast it was going when it ran off. Okay. Big things to remember there is if you go off horizontally, the initial vertical velocity is 0. Okay, and then after that it's just acceleration in v equals d over t. Okay, and right. So we could have one like this, and in the question, I would give you like the angle, and I would give you the projected velocity.
Isn't the max height only halfway through?
Yeah, that's what we said.
No, but what about when you like land a lower height or higher?
Oh, we're not going to have. We always worked on ones that were level.
Oh yeah.
Yeah. Okay. But you're right. If it was shot off of a roof and hit the ground down below, then yeah, the maximum height is not halfway through that. Yeah. Okay. So for these ones here, like I say, I would give you the projected velocity more than likely and the angle it was projected at. Okay. Which then, of course, you use that triangle to get the horizontal component, which will be your horizontal velocity because this is a velocity. Okay. And your vertical component would be your initial vertical velocity, because obviously the velocity is going to change vertically because it's affected by gravity. Okay, so lots of things can come into play here. Okay, acceleration formulas, maybe to get time. Okay, then you use that to get the distance traveled. You could be asked about maximum height, so you might have to use VF squared equals VI squared plus 2AD, or D equals VIT plus 1/2 AT squared. Okay, you could use that one as well. Okay, lots of acceleration formulas and vector components coming into play with those projectile questions. Okay, is that ringing a bell? Okay, so that was it. That's what's in this unit. Okay, is just doing those kinds of things. So it was kind of the fundamentals for the rest of the course. Okay, so for unit 1, scalars and vectors, V equals D over T, graphing, probably the biggest part, projectile motion probably be the second biggest part. Okay, vector addition, that's in more than one unit. Okay, so it's also pretty significant. Okay, like I said, this was the building blocks for unit 2 as well. All right, questions from you guys? I have a few practice questions up here we can go over, but I'd rather answer questions you had before we get to the rest. Okay. How many people started doing the review package? Okay, I get it, it's the last test, but get on it sooner rather than later. Okay, don't wait too long. Okay, velocity versus time graph. Here are the things I would like you to solve for. There are the answers. I didn't show you how I got any of them, but there they are. Okay. Oh, boat question. Okay, that's a good one. We haven't done a boat question for a while. All right. So the river is 50 meters wide. You are rowing across at 3 meters per second. The current is 5 meters per second downstream. I would like the resultant velocity, that would be this side, I would like the resultant velocity, and I would like to know how far downstream, this here, okay, how far downstream you are when you get to the other side. Okay, let's see what we remember about the boat question. Okay, so calculating the resultant velocity is just vector addition. We put them tail to head. We just have to do Pythagorean theorem and a trig calculation. Okay, we're looking for this angle and for that number. Okay, so the magnitude of the velocity is just going to be 5 squared plus 3 squared. Okay, so 5. Whoop, I need the square root sign there. Square root of 5 squared plus 3 squared. Okay, it's giving me 5.83 meters per second. All right, I need theta, so for me that's going to be opposite over adjacent, inverted. Okay, so that's going to be 5 over 3. Okay, so that angle's 59 degrees. Okay, so my final answer there I only have one significant digit, so I guess 6 meters per second at 6 times 10 to the 1 degrees. And that would be, I don't know, I could probably give compass directions on that, or from the center of the river, or east of north. Probably would have given me compass directions if it was on a test. Okay. What if I asked you for the directions relative to the shore? Would you use that 60 degrees? No, you'd find this one, right? It'd be 30. Because I added them right that time, it added up to 90, not 100. All right, and the other thing, how far downstream will it be when they get to the other side? Well, if I'm going to find D and I know V, that means I need the time it takes to get across. I am not going to use this to get that. Okay, that will not help me because that doesn't point across or down. I do know how wide the river is, and I know how quickly I'm going that direction. So time would be D over V, and that would be 50 divided by 3 meters per second. So that would get me the time to cross. So the time to cross is just over 16 and a half seconds. Now, that is also how long I am going downstream. So I can take D and go V times T to figure out how far downstream I go now that I know how long I'm going downstream for. So I simply multiply that by the downstream velocity, and I would have 8 times 10 to the 1 meters downstream for my final answer, because I silly made it one significant digit, which of course I wouldn't do on a test. All right, questions there with the boat question? Okay, so it's just important to note how we put the vectors together. We always draw them tail to head. No, that's a spring constant question. Well, then we've got dynamics already. Okay, any questions from you guys that you would like to go over from the kinematics unit? Any question types?
Projectile motion.
Yep. Well, we can do a projectile.
Is there gonna be a boat question on the final?
Never know. I'll give you some detail, but I'm not going to tell you everything. And
Would it be a question of one sigma?
no, that I won't do. Okay, so in this question, our projectile has been launched at a velocity of 150 meters per second, 18 degrees above the horizontal. Okay, what I want calculated is, or are, okay, time it's in the air, horizontal distance, and max height. Okay, so let's have a look at this one here. So obviously we need to first calculate the horizontal component, okay, of that projected velocity, because that will be our horizontal velocity. And we're going to need also the vertical component, because that will be our initial vertical velocity. We know, of course, that the projectile is going to follow an arc. It's going to have it re-encounter the ground over here. Okay? So we're going to have our vertical part and our horizontal part. Okay, so vertically speaking, okay, right now I know the acceleration, negative 9.81 meters per second squared, and I can calculate VI. It's the adjacent, or sorry, the opposite side, so I'm going to go sine of 18 times the hypotenuse, which was 150, and that will give me my initial vertical velocity. All right, so sine of 18 times 150, and it's 46.35. I'll keep all the decimals. Positive 46.35 meters per second. Since it hits the ground at the same height it was launched from, what's VF? Nope. It would be 0 at the maximum height. I'll use that later. It's negative 46.35, right? What goes up must come down. If it does the same thing up and down, it's got to come back at the same velocity, just in the opposite direction. Okay, if I have those three pieces of information, what can I calculate? Time. That's the first thing I was asked to calculate, the total time in the air. I've got VF, I've got VI, and A. So time is going to be VF minus VI over A. So that'll be negative 46.35 minus 46.35. And divide that by negative 9.81. And we'll get our time. So 46.35 times 2, I'm just going to shortcut, guys, because that's what it would come out to, divided by 9.81. All right, so this is going to be in the air for 9.45 seconds. Rounded, of course. I'm going to keep all the decimals. 9.45 seconds. Well, now I can bring that over here. Time applies to both sides. Okay, the second thing I wanted was the horizontal distance traveled. Well, in order to get that, I've got to know how fast the projectile is traveling horizontally, which I can calculate because I'm given this stuff here. All right, so I'm going to go cos of 18 times 150. All right, that'll give me my horizontal velocity. And it is 142.66. meters per second. Okay, now that I know V and T, I can calculate D because horizontally it travels at a constant velocity, so it's just V times T. So the 142 with all the decimals times 9.45 with all the decimals. All right, so we're looking at 1.3 times 10 to the 3 meters. Okay, this time would also, if it was part A, I would actually, if it was part A, which it is, I would use the rounded value in part B, so that would probably come up to something different. I would use 9.4. Okay, so we've got that, and then the last thing we're supposed to find is the maximum height. Well, the maximum height either occurs at half of the time or when VF is 0 meters per second. So you can do it one of two ways. Okay, you can do this. VF squared equals VI squared plus 2AD and solve for D. So VF squared minus VI squared over 2A. So that'll be 0 minus then 46.35 squared divided by 2 times negative 9.81. Okay, so if we do that, so 0 minus that number squared, okay, divided by negative 9.81. All right, so the maximum height's going to be 2.2 times 10 to the 2 meters. Okay. Or I could also do this. D equals VI times T plus 1/2 AT squared, but I have to use half the time.
Would you also need to divide that by 2 because it's divided by 2A, not just 3.
Didn't I do 2 times 9.81? Oh, I messed up. My fault. Oh, you're absolutely right. So negative 19.62. Good eye. Divided by negative 19.62. 109 seconds, okay? Well, actually, 2 significant digits, 1.1. Okay, so 1.1 times 10 to the 2 meters. Okay, and if I do this, it's the same thing, but I have to use half the time. So instead of 9.4 seconds, I would use 4.7 seconds. Okay, so I take that VI, which is way up here now. times 4.7 seconds plus 0.5 times negative 9.81 times 4.7 squared. Okay, gives us pretty much the same number. Okay. Everybody all right with that? So more than one way to do that maximum vertical height part. Okay, I would expect something just like that on your final exam. Okay, that tests everything but graphs from the first unit. There's some vector components there, acceleration, v equals d over t, okay, all of that stuff. It's a great way to test basically the whole unit in one question. All right, what else would you like to go over from unit 1? Okay, well, if you don't have any questions, my suggestion to you would be look at the review package I posted last week. Okay, since all of you appear to have your phones, since none of them are in the pockets over here, okay, I would bring that up on your phone from Google Classroom and start trying a few of the questions from there. They're all pretty much exam level questions, so you can give them a try. And then if something comes up, you can ask. My plan is tomorrow to go over dynamics, okay, and maybe a bit of circular motion. We'll see. And then have your unit exam Wednesday. Thursday we go over the unit exam and then do whatever circular motion review we need. It was a shorter unit, so I figured we could probably get it done on Thursday. So today was kinematics, tomorrow will be dynamics, Thursday will be circles. Okay, we don't need to do a unit exam review for unit 4 because we just did. Okay. All right, well, that is my suggestion to you right now. If you're reading a book, put the book away and get to work on your review stuff for physics right now, please. Okay, and if more questions come up, please ask. That's what we're here for.